at something called the discriminant. And the word is not discriminate, it's discriminant, and A-N-T there. And it's going to be misspelled if you type the word, so it's not like one of those words that's going to come up as a regular spelling word. It's a mathematical term. And the idea behind the discriminant is, if you look at the quadratic formula, there's a certain part of the quadratic formula that indicates something for us. And based on that part of the quadratic formula, we can determine, the characteristics or the nature of the roots of the equation. So, can somebody please just tell me what the quadratic formula is first? Oops. What's the quadratic? Yeah, what do you got? So we all have this memorized now, right? Should all make sure we have this equation memorized. I'm going to put roots instead of x, because it could be y or z or whatever the variable is. Now, what would it take for these roots to be imaginary roots and not real roots? What would cause these roots to be imaginary? Yeah. A negative under the square root. Well, if you look at the square root here, Mike, what do you see under the square root? So if that whole thing is going to be negative for it to be imaginary, we could say in terms of inequalities that it's less than 0. When this quantity is less than 0, we're going to end up getting imaginary roots. What if this quantity is greater than 0? The whole quantity b squared minus 4ac is greater than 0. What kind of roots do we have? Instead of imaginary, we have real roots. Now, we can be even more specific, and we can go through more situations with b squared minus 4ac. So that's the goal of today. So when we do the first example, we're going to calculate b squared minus 4ac. We're going to jot that number down, just as like a side note. Then we're going to use our calculator program to find the roots, and we're going to talk about how the discriminant matches the type of roots that we get as an answer. All right, it's going to give us the nature of the results. So let's take that's what I was just talking about. So all that stuff I just said in the last part is on this slide for you right here. So really we're looking for, again, b squared minus 4ac. And this is what I was talking about, the word discriminant, distinguish. It helps you distinguish between the roots. Okay, whether they're real, imaginary, rational, irrational. So let's look at the first one. Go ahead, use your program, please. Come up with the roots for this one. Making sure that you remember negative signs where applicable. So I'm going to calculate b squared minus 4ac every time. Okay, in this case, I'm going to get 41, it looks like. 4 by 4 is 16, 9 and 32, yep, 41. So the discriminant in this case turns out to be 41. What do you get for roots here, Ryan? When you ran it through your program, what did you get?
Negative 2.3. And then
0.8? Did you only get one decimal? 0.9? Are you rounding or?
I just rounded.
Okay. So you got negative 2.3. I have negative 2.35 written down. Did I round to get that?
Yeah.
So should it be 2.4 really?
No, it's 2.350.
350? Okay. So if I rounded, it would be 2.4, but I'll do 3.5 then, if that's exact there. And then 0.85?
Yeah.
They are exact, right? They're not going on forever? Are these numbers continuing? Are there more decimals beyond? Okay, there are. That's what I'm asking. All right, thank you. So these are my two answers in this case for you, right? Those are the two types of answers. But what we'll notice is that the decimals in these answers continue. Now, do they continue with any repeatable pattern? Take a look at the decimal on your calculator. Is there any part of the decimal that repeats itself? Like remember sometimes you get like 684, 684, 684, and you put a bar over 684. There's nothing like that, right now? What kind of numbers do you call those? when the decimal goes on forever but with no repeatable pattern?
Irrational.
Irrational. All right, so let's jot that down also. So we have irrational roots when our discriminant was 41. The roots are both real numbers, so we can write that down as well. Okay, we'll list our characteristics on the right side there. So that's what we know so far about this one. All right, pretty easy. That's all we're going to be doing for these, and then we're going to come up with some conclusions. We're going to draw some generalizations from this, from these examples. Let's go to the second. For the second one, list A, B, and C. Run it through your discriminant. Come up with your roots. And by the way, obviously everything is divisible by 2. Notice for this, it says determine the zeros of the function. When it says find the zeros of the function, what does that really say? Because it's a different wording from the last one. The last one said determine the solutions to the equation, and it was an equation that was set equal to 0. This says find the zeros of the function. Mike? Yeah, so what do you do, Mike? What's the first step, really? What should I do with this? Instead of putting f of x, what should I replace f of x with? Help me? 0. Remember, the zeros of a function is saying when is the y value 0, really. So really what we're doing is this, which is what enables us to write 2, 12, and 18, and then go through the quadratic formula. Remember, it's got to be set equal to 0 for this to make sense. So go ahead and calculate your roots from this on your calculator. I'm going to say discriminant equals b squared minus 4 times a times c. And that's going to give me 0, actually. I'm going to get 0 for the discriminant. I get 0 for the discriminant. What do you get for the roots in this one? Charles, what did you get for your roots? Did you run it through yet? No. Nah, what did you get? -3 and -3. So, the root is what? What's the word? When you get 2 of the same roots, they say what root? Double root. Very good. Or generally speaking, a repeated root. It could be a triple, it could be a quadruple root, but in this case, it's a double root. Agreed? A double root, does this make sense? So we have a double root here. Well, you have a double root. It's not imaginary for sure, but it's not irrational. It's definitely rational, right? In this case. So we have a double rational root. Let's jot those words down. Double rational root, or repeated rational root. All right? Let's go to the third case. So in this case, we're finding the roots of the equation. So we can start right away. There we go. Again, the 0.816 that goes on forever with no pattern indicates that it's irrational. That comes about from the fact that this is 24, not the negative part. The negative part indicates that there's going to be an I in the answer. So for these roots, how would I classify them? What term would I use?
Imaginary, irrational.
Imaginary, for sure. And they're irrational. But what was the term that indicated that I have 1 plus something and 1 minus something? We've been doing this when our denominator is irrational. We multiply by the blank blank. Yeah, now in this case, it means since it's imaginary, it wasn't called, we called the other ones binomial conjugates. For the imaginary, like 2 plus I, 2 minus I. What were those called? Anybody remember that term? It wasn't binomial it is a binomial conjugate, it is. But more specific than that.
Complex conjugate.
Complex conjugate, okay? Both words are good, really. It's the same thing in this case because they're both binomials. But complex means that it's imaginary. So instead of writing imaginary, we could just write that these roots are complex conjugates. Okay, they're complex conjugates, which, yes, that is imaginary, but I know that now not only are they imaginary, but they come in pairs. They come in pairs. Whenever there's a plus, there's going to be a minus. Whenever it's imaginary. Why is that? Think. Think about it. Where are these roots coming from? Why is there a plus imaginary and a minus imaginary? Where are the roots really coming from? What formula?
It's from the square root of negative numbers has to be equal to positive or negative number squared.
You're kind of saying it right, kind of not. This is part you're missing still. It is a square root of negative number, so it's definitely I, but that doesn't make it a plus or minus. Look at the formula. Make it easier. You're thinking too much. What does the formula physically say? The quadratic formula. It says plus or minus, doesn't it? Look, ready? Negative b plus or minus square root, negative b plus minus the square root of b squared minus 4ac. Now I'm going to separate it. I'm going to put them over 2a individually. Even though it's all over 2a, I can do this, right? Think about it. This is a common denominator. So I could write it like this, or I can write it all over 2a. It's the same thing. Well, look over here. This part is always going to be what? Give me a type of number I'm always going to get. Always. What kind of a number? Real. Be careful on the rational. I would say yes, but what if b would happen to be like radical 3? Like what if the coefficient b was square root 3? Then you get square root 3 over some number, which would be irrational. So we know that this will be real, though. This will definitely be real because b and a are never imaginary themselves. Even if a or b were negative, it makes this part real. So go back up to your answer. Remember here, this part is real. This part is real. That comes from this part right here. Let me get rid of this. Hold on, let me move this all the way down. There we go. So this real portion, this 1, comes from negative b over 2a. The imaginary portion, which has a plus or a minus, comes from this piece here with a plus or minus. Does that make sense, what I'm getting at right now? Based on whatever's under the radical, if this is negative, it means that this is going to be imaginary. You're going to get plus or minus, so you're going to end up with complex conjugates for this third case. So let's take these ideas and give me a statement or some statements I can write. What types of discriminants did we have a minute ago? The first case, the discriminant was what? Give me a word to describe the discriminant in the first case. Positive. The discriminant, I'm saying, just the discriminant. Right? Look at example 1. Example 1, the discriminant was 41. I'll write it down over here. We'll put our answers, okay? The discriminant was 41. And the roots from example 1 were negative 2.35, and 0.85. When I put ... I'm indicating that it goes on with no pattern. If there were a pattern, I would use a bar above it. Okay, and obviously this is not exact, this is an approximation because it's irrational. So, what we notice though here is that the roots are definitely real. Okay, we know that the roots are real for sure. Now, in this case, we know that there's going to be 2 different roots. In the second case, what did we get? What was example 2? What kind of roots did we get there? Look at your roots. What was it? A double root. So we really, in the second case, get 1 repeated root. Like we call that a double root. So for positive, we're going to say we get real roots. There are 2 of them, and they are distinct. What does distinct mean? Different. Okay? 2 real different roots. 2 real different roots. We'll talk about the irrational portion in a minute. Let's leave that off for a second. For the second case, when the discriminant were equal to 0, remind me again, Charles, you just said it, but when the discriminant equals 0, what did we get? A double. And we could say double root or 1 repeated root. Either one is the same thing. Okay, double root works for me. A lot of books have a tendency, and I don't know why this is, to write 1 real repeated root. Okay, same thing as a double root. Now, what else did we notice about that root? Specifically, if you look at the quadratic formula and we look at our discriminant, the discriminant was 0. The discriminant was 0, and the roots were -3 and -3. So, for this example, you can definitely say that the roots are what kinds of numbers also? What kinds of numbers?
Integers.
Okay. You can't always say integers, but be more general than integers. What's the one above integers?
Real numbers.
Between real and integers, you're forgetting a type of number.
Rational.
Rational. Let's talk about why that is. Okay? Let's write rational. Let me talk about why that is. Or what the case would be. So let's pause for a second and look at these first two cases. So let's write down our quadratic formula again. I'm going to write them each over 2a again. And I'm going to do this for a reason. Now, in the second case, what was the discriminant equal to?
Yeah.
So what happens to this whole thing?
Uh,
If this is 0.
The root is 0.
Yeah, and what's 0 over anything still?
0.
0. Agreed? Case 2, the entire right-hand side of the quadratic formula drops off. So over here, this entire thing is gone. So in your mind, or just do it real quick, do that. If that were the case, what are you left with? You're left with negative b over 2a plus or minus 0. Well, what's 5 plus 0 and 5 minus 0? They're both still just 5. There's no change. So as a result, whenever the discriminant is 0, as you can see here, you end up with just negative b over 2a as your repeated root. That's why your answer was negative 3 and negative 3. If you go back to example 2, what we had was the following. b was 12 and a was 2. So if we plugged in our roots for example 2, we ended up getting ready. b was 12, so negative 12 over 2 times a, which was 2, plus or minus 0. Well, look back at example 2 now. This is the work we had. Negative 12 over 4 is going to give me negative 3. That's where my answer comes from. Now, I know that if I divide two things, it's definitely rational, unless one of those things happen to be a square root. Again, if b in the original, imagine the equation was the following. 3x squared plus radical 2x minus 5. Well, then in that case, b would be radical 2. And then you would have negative radical 2 over 4, and it would be irrational. So if we are making the assumption that a, b, and c are rational, real coefficients, this answer will always be rational for case 2. Again, if a, b, and c, all those coefficients are real and they're rational, either they're a fraction or they're an integer, but they're not a radical of some sort, then we're always going to get a rational answer when the discriminant is 0 because this whole thing drops off. Is that clear? Now, let's go back up to example 1 before we get to example 3. The discriminant was 41. Mike, what's the square root of 41? You have any idea? No, why not? Because it's irrational. But what if the discriminant were 36? Then you'd have to do radical 36, right? And isn't that easy to do radical 36? What's the square root of 36? 6. So when the square root of a perfect square occurs, you're going to end up getting rational roots. But when the square root of a non-perfect square occurs, you get irrational roots, right? So look at this discriminant up here. If the discriminant is positive, we know that the roots will be real, there'll be 2 of them, and they'll be different. But we can subcategorize. We could say if it's a perfect square, then the roots would be rational. If it's a non-perfect square, the roots are going to be irrational. Since 41 was a non-perfect square, we got irrational roots. And that comes about because of the fact that you can't take the square root of a non-perfect square. Had this discriminant been 81 instead of 41, made life a lot easier. You would have had a 9 here. 9 over whatever 2 times a is definitely rational. It would be a fraction. Fractions are rational. So we subcategorize the first category. If the discriminant is a perfect square, it's rational. If the discriminant is a non-perfect square, it's irrational. Make sense? Let me know if it doesn't. If it's confusing, I'll try to explain it with another example. I can do that, but I don't want to, drive it home 10 times if you get it. All right, let's go to the third case. When the discriminant in the third case is what kind of a number? Negative. When the discriminant is negative, we get complex conjugates. And that's all we really need to write. Because if we write complex conjugates, we know it means 2. Because the conjugates, whenever it's conjugates, it's 2. And the word complex means imaginary. It means that there's an imaginary and a real part already. So as a result, we're always going to get complex conjugates. Now, you really don't have to categorize this one into rational and irrational, but you can. But it's traditionally not written. It doesn't matter. So if you get like 1 plus radical 2i and 1 minus radical 2i, they're complex conjugates and they're irrational. But usually once you write complex conjugates, there's no need for any more categorization. Okay, it's just almost like one of the common ways that you just write it. Okay, so you don't need to break this into categories like this. But you could remember, obviously, that if your discriminant is 4ac, although being negative, if it's still a non-perfect square, it would end up being irrational as well as complex. But I'm not going to quiz you on that or ask you about that. All right, now, with that stated, let's take a look at perfect SAT problem. Obviously, you're not going to do 3 parts, but the skills you need in this problem could be easily tested on an SAT. Okay, this, and actually the next one too. Oh no, this one more than the next one. So, the equation kx squared plus 8x plus 4k equals 0 has different roots for different values of k. Does that make sense? If k is different, it changes what a and what c are. So as a result, we want to find the values of k for which the equation has the following stuff. So, when will there be a double root? When is there a double root? What category was that? Go back to your last slide, look at your table. When did we get a double root? When the discriminant was what?
Positive.
Not positive, a double root, Mike. A double means repeated. Which part had a repeated root? Look at your table. The middle row, you should have labeled. Yeah, you should have labeled that 0 and then double root or repeated root. Make sure you're writing that down. So a double root is when the discriminant is 0. So what we can do in this problem is set the discriminant equal to 0. What's the discriminant though? In this case, what's b squared minus 4ac? Luca, give me. Just tell me. What it,
So it's 8 squared minus 4 times k times 4.
4 times k times
4k.
4k. Remember, k is not a variable. That's misleading, I know, right? K is not a variable. K is a number. So 4k itself is a constant. Imagine k were 2 or 5 or 7, right? Then you would have a number at the end there. So the quantity 4k is what c is. So we set that equal to 0. Divide everything by 16. This is part A, obviously, that we're doing here. Now, I can solve this 2 ways. Give me one way to solve this, please. Sabine, what's one way to solve this? That's fine. You can say factoring for this, yeah. What would you put? Go ahead. Yeah, this is difference of 2 squares, right? So we could solve it this way. How else could I solve this? How else could I solve this? Somebody different? There's another way to solve this? How would you solve any other normal equation? Move everything over to one side, that's not a variable, right? So Ben, move everything over, what do you get?
You get 4. Yeah.
So what's k as a result, Ben?
2.
Be careful, Ben. You're taking a square root.
Oh, plus or minus.
Yeah, remember you're finding a solution to an equation. When you take a square root, you get the principal root and the negative. And that makes sense because here, look, you get k equals 2 and k equals negative 2. So my answers are plus or minus 2. So if k was 2 or if k were negative 2. Can't be both, right? You can't make one of them 2 and one of them negative 2. Either both of those k values in that equation were 2 or both of them were negative 2. That would yield a repeated root. Now, part B says 2 different real roots. Look at your chart. Look at your chart. Ryan, the chart. Which category in the discriminant chart told me that I can get, again, look at part B here, 2 different real roots if the discriminant is what?
Discriminant is positive.
Positive. So I'll say greater than 0. Does that work? Right? Positive is greater than 0. So I'll write it like that. So now we're going to take this expression down here. We simplify, right? Right here. See the simplified form right here? And just instead of an equal to 0, we put a greater than 0 symbol. So I'm not going to do all the work again. Why would I want to rewrite it? I'm not going to rewrite it from the beginning up here and do all this work. So go from here and rewrite it for part B the same way. But instead, write 4 minus k squared is greater than 0. I'm going to factor it again, like Sabine mentioned earlier. So, when two factors are greater than 0 instead of equal to 0, when I solve, I don't get the solutions, I get the what? What are they called? Think about your vocab from chapter 4. Critical points, very good. Got to go back, chapter 4 is why math is so cumulative. You get 2 answers here. Yeah, k equals 2 and k equals negative 2, but we call these the critical points. And we have to test them. Where do you test critical points? On a number line. So we want to know which regions, remember these are 3 regions here, are greater than 0. Which of the 3 regions, the middle one or the outer 2, are greater than 0? So test the middle one. Why am I going to test here? Somebody tell me why I would test the middle first. 0. Plug in a 0 here and here. You get 2 times 2, right? Plug in a 0 here. Plug in a 0 here. You get 2 times 2, which is positive. So this region is positive. Anybody remember what the trend is going to be?
So less than which is going to be negative, and greater than negative. Greater than 2 is going to be negative.
Yeah, these are both going to be negative. So as a result, we wanted to know for part B, when this inequality is greater than 0, or when this expression rather, when the whole inequality itself is a greater than, or when this expression is greater than 0. Well, it's greater than 0 in that middle region. So for part B, my answers are open circle, shade, open circle. Why are they open circles? Because it's simply greater than, not greater than or equal to. Remember, if k is equal to 2 or negative 2, that's the answer from part A. Remember part A, the answer was 2 or negative 2. Part B, it's going to be between 2 and negative 2, but not including 2 and negative 2. So, Charles, solution set. How would I write that in solution set form?
So k has to be, you could write negative 2 is less than k, which is less than 2.
Very good. Okay, interval notation. Interval notation. Anybody remember interval notation? It's either parentheses or brackets. When it's an open circle, it's parentheses. Wherever you start and wherever you go up to, and then you close. This is not a coordinate. This is not a coordinate. This is interval notation. This is solution set form. Same answer. This is telling me from negative 2 all the way to 2, not including the endpoints. These parentheses come from the fact that these are just less thans. Had they been less thans or equal to, there would be brackets right here instead of parentheses. Third case. Case C says, how would we get imaginary roots? Real quick, just tell me. What would the discriminant have to be? Negative. So we would do the same thing. 4 minus k squared is less than 0.